Let's add a twist to the example where we had a sphere of charge that was uniformly distributed throughout the volume. Let's take the same sphere, but let's drill a hole out of the center. That means we have a thick spherical shell. If you wish, you can try and imagine something like a bowling ball with really thick walls but an empty center. So we've got this thick shell. Inside the shell is an empty sphere, nothing at all inside here. The inner radius we'll call A, the outer radius we'll call B. We want to find the electric field as a function of distance from the center of the shell. So starting here, what's the field in this area, and then outside the whole thing? Begin with Gauss's law and show all steps. So let's start by writing down Gauss's law. It says that the net electric flux through any closed surface is the integral of the electric field dotted with the area, and it's also equal to the net charge enclosed by that Gaussian surface divided by epsilon naught. Let's start by dealing with this term. We have spherical symmetry in our charge here, so let's make a Gaussian surface that applies to that spherical symmetry. So if we have a charge with spherical symmetry, it means that the electric field lines are radially outwards. If our electric field is radially outwards, then our best choice of a Gaussian surface is a sphere. We'll call that radius r. So that's our Gaussian surface. It's a sphere with radius r. So then when we write our net electric flux, the integral of E dot dA, we'll have to identify our dA. That's a little bit of area on the surface of our Gaussian sphere. The area vector comes straight out, so dA is straight out, electric field is straight out. Those two vectors are parallel. So E dot dA is E times dA times cosine of theta, where theta is 0 because they're parallel. We've got the integral of E times dA. Because of our spherical symmetry, our electric field is constant everywhere we're the same distance from the center. So everywhere on this surface, the electric field has the same magnitude. E comes out front of the integral, so we've got E times the integral of dA. The integral of dA is the area, A, which is 4 pi r squared, area of a sphere. Okay, so the integral of E dot dA with spherical symmetry is equal to E times 4 pi r squared. Don't forget the squared. Okay, so now we've dealt with the integral part. Next we have to deal with what's the Q inside for each one of these three regions. We need to find our electric field in three places. So let's start by finding the electric field inside the cavity. So where the radius of our Gaussian surface is less than the radius of the inner wall of that shell. Let's draw our Gaussian surface. It's going to be a sphere with radius r less than a. Let's apply our Gauss's law. The integral of E dot dA is equal to Q in over epsilon naught. What is Q in? Well, Q in is how much charge is enclosed by this green circle we just drew. Let's remember that the cavity within the shell is empty. There's nothing inside here. That means there's no charge inside there. So Q in equals 0 because there's nothing in there. So E times 4 pi r squared equals 0. The electric field for r less than a equals 0. Okay, there's the first bit done. So we already found the electric field inside here. It was 0 because there's no charge. Next bit is what is the electric field inside the insulator itself, so in between A and B. So let's pick a Gaussian surface that has a radius that's bigger than A, but it's smaller than B. So we'll draw our Gaussian surface here, sphere with radius between A and B. We're going to apply our Gauss's law. The electric field, the integral of electric field dotted with the area is equal to Q in over epsilon naught. This time we have to do a little bit of work for Q in. So Q in means how much charge is inside this blue circle that we just drew. So we have to ask how much charged object is inside, because we know there's no charge in that white space, but there is some charge in this part we're shading in right now. It's not the total charge, it's only part of the charge because it's only part of the surface. So for our Q in, because this is a 3D object, we're going to do the volume charge density. So our density, that's given with our symbol of rho, and we have to multiply it by the volume of the charged object inside the Gaussian surface. Okay, we know that the white space doesn't have any charge, so it's only this bit here that has charge, so we have to find the volume of this bit. Okay, so the density, that's easy enough. That's rho. How are we going to find the volume of this bit right here? Well, we can imagine this as a sphere with this volume right here. Subtract this sphere right here. So if we imagine this as a solid sphere, we take away this center, we get the volume of what's left over. So that's going to be multiplied by 4/3 times pi times r cubed. That would be if our Gaussian surface was a solid sphere, if the whole inside bit was charged, but it's not. We have to subtract the bit with no charge, which is 4/3 times pi times a cubed. Okay, now we put it all together. So our integral of E dot dA is E times 4 pi times r squared. That's going to be equal to our net charge, which is rho, times 4/3 times pi times r cubed minus 4/3 times pi times a cubed, and we have to divide the whole thing by epsilon naught. Okay, there's close to our answer. Now we want to solve for E. I think first I'll try and simplify my algebra a little bit by taking my 4/3 pi outside. So I've got rho times 4/3 pi times r cubed minus a cubed. That's all divided by epsilon naught. Now I'll divide both sides by 4 pi r squared. So E is equal to rho times 4/3 pi divided by epsilon naught. I'm going to divide my 4 pi here. And then I've got r cubed minus a cubed, put my r squared over here. So I've divided both sides by 4 pi r squared. Let's see what cancels. 4 on top and bottom cancels. Pi cancels. And right here, r cubed divided by r squared is going to give me r here. And I'll have a cubed divided by r squared here. So my final result is E is equal to rho over 3 epsilon naught. Outside of r cubed over r squared is r. Subtract a cubed over r squared. Electric field is a vector, so the direction is going to be radially outwards. The last area to find the field now is outside the whole thing. So let's draw a Gaussian surface, which is a sphere with radius r bigger than b. Not a perfect sphere, but hopefully you're getting the idea there. So there's r. We'll apply Gauss's law, and net electric flux is the integral of E dot dA equals Q in over epsilon naught. We have to figure out what is Q in. So we ask what charged object is inside our Gaussian surface. Well, that would be our thick spherical shell. So our Q in is however much charge is on this spherical shell. And since the whole shell is inside, we need the charge on the whole shell, not just part of the shell like last time. So that's going to be the density of the shell times the volume of the shell. Density has our symbol rho. Volume of the shell will be a sphere with radius b. Take away a sphere with radius a. So it would be this whole big thing if it were solid, subtract this inside core. So it's density times 4/3 times pi times b cubed minus 4/3 pi times a cubed. If you wanted to simplify that right off the bat, you could say rho times 4/3 pi b cubed minus a cubed. Okay, let's put our Q in together with what we know for E dot dA. So E times 4 pi r squared, that's our net flux, equals our Q in, rho times 4/3 times pi times b squared minus a cubed. And then our net charge has to be divided by epsilon naught. Okay, we've got to spill on to the next slide. So we'll divide both sides by 4 pi r squared. E is equal to rho times 4 pi over 3 times epsilon naught. That's what we had originally. Now we'll divide by 4 pi. And I'm going to put my r squared under my b squared minus a cubed. B squared minus a cubed over r squared. Okay, I think I got all my terms written down there correctly. Let's see what cancels. The 4's cancel and the pi's cancel. That leaves us with an expression for our electric field equal to rho over 3 epsilon naught outside of b squared. That should be b cubed. My goodness, I dropped a cubed there in my last slide. Okay, we'll fix that up. B cubed minus a cubed, because the volume was 4/3 pi b cubed. I just wrote a squared by mistake. So I've got b cubed minus a cubed divided by r squared. There's our electric field. Because it's a vector, we'll say that the direction is radially outwards. Okay, so now we found the electric field in each of the 3 spots. Part B is make a graph of this electric field. For the last bit of this problem now, we're asked to make a sketch of the electric field. You don't have to do it perfectly. You might notice that I sort of cheated and filled in the line here ahead of time. That's so I could draw it better on the slide. I went ahead and I plotted it using Excel just to get a really nice look of what the picture is. But you can certainly just draw a general shape when you draw this for your answers. So we know the electric field in 3 spots. If r is less than a, the electric field is 0. If r is between a and b, it's rho divided by 3 epsilon naught times r minus a cubed over r squared. And if r is bigger than b, we know that the electric field is rho over 3 epsilon naught b cubed minus a cubed divided by r squared, where the electric field is non-zero, it points outwards. So for r less than a, let's just drop a line down from our sphere. We know that the electric field is 0. That bit's easy to fill in. So it's just a line where E equals 0. So that's at the beginning here. For R between A and B, that's in the solid part of the insulator, it increases from 0 to some maximum value. So it starts and it goes up. This is sort of a funny shaped graph, r minus something divided by r squared. So we know it's going to increase, but we figure it has a bit of a curve to it. So as you draw it increasing, and you can add in a little bit of a curve. So there's our electric field line increasing. Increases to some maximum value. The maximum value is going to be when r equals b. And that gives us rho over 3 epsilon naught times b minus, I'm sorry, someone's barking outside, so Pippin is trying to help out, divided by b squared. He'll stop in a second. Okay, and we can get that same expression for the maximum electric field. This is our maximum. If we plug b into this equation or this equation, they both give us the same maximum field. Okay, for r greater than b, we see that it falls off as 1 over r squared, so it falls off more or less like this. And as r gets big, eventually E goes to 0. So there's a decent picture of what the electric field looks like as a function of distance from the center. This is a homework question. It's very much like where we did an insulating sphere of charge, except now we have an insulating cylinder of charge. You're going to follow the same steps we did for our sphere, but this time you'll use cylindrical geometry. I will post the answers for this as well so you can compare what you get to what I get.